I'd like to begin. I'm Jeffrey Linsky. I'm a rhino. Anybody know what a rhino is? Rhino means retired in name only. So I'm retired from the University of Colorado, but I still work full-time or 70 hours a week or whatever it is, and enjoy doing science with no employer, no supervisor, no responsibilities, and no paycheck. Okay.
You're still Brian's mentor, aren't you?
Well, he graduated a long time ago, so he does his thing, but we collaborate quite a bit. Okay, this is a tag team, and Brian gave you the first half of the talk pertaining to essentially astrospheres' interaction with the interstellar medium. I'm going to give the second half. Brian was talking primarily about what you see from the inside of the heliosphere, and I'm going to talk mainly what you see and can learn from the outside of the heliosphere, the interaction of the stuff around us, around the heliosphere, and how it affects the heliosphere itself. And I welcome questions. I'm told I could go over 45 minutes. I've been in this business a long time. I enjoy going longer than the allowed time because I do it all the time. Okay. There's a lot of material in here that is almost certainly unfamiliar to people in the solar physics domain. What I'm talking about is the interface between solar physics and astrophysics. The two fields have different jargon. I'll attempt, when I'm talking on the astrophysics side, to use terms that are familiar to solar physicists, and if you're don't understand the terms, please ask. And when I'm on the heliospheric side, I'll try to talk in terms that make sense to the astrophysics side. So this is interface science. Okay. I have a lot of things to talk about. Some of the slides I'll show, I want to go through rapidly, just sort of motivation. You can all guess what the motivation might be. And then on a number of these slides that I consider really important, let's stop, look carefully at what's being presented, ask some questions, and try to get it understood. Okay, briefly through motivation, the sun and its heliosphere lives in a highly inhomogeneous environment that is changing. Not rapidly changing, but changing by huge orders of magnitude. So the environment of the heliosphere today is not the same as the environment in the past, and it's not the same as the environment in the future. There are going to be big changes. Right? There have been big changes. Of course, the interstellar medium is very important because we are made out of interstellar medium material. Okay? Everything except hydrogen in our bodies is from stars, supernovae, etc. Okay, I'm going to talk about heliosphere, and I'm going to talk about the interstellar medium, its various components, its temperatures, densities, structures, and how it affects the heliosphere. I'll even mention that we may be moving from one element of the interstellar medium into another element, in which case things are going to change. Okay, and the objectives of much of the work that I've been doing with Brian and Seth Redfield at Wesleyan University is basically to characterize the interstellar medium so we can come up with an effective boundary condition to models of the heliosphere. And I mentioned a few papers at the end. So let me start, and now I'll go slow and try to put this all in context. What you see here is a model of the universe in galactic coordinates. I'm going to be talking a lot about galactic coordinates. Galactic coordinates, latitude, longitude, relative to the center of the galaxy, which is right here. And longitude, this is the anti-galactic center direction, 180 degrees away, and that's the North Galactic Pole. So all the diagrams you're going to see are going to be in these units, these coordinate systems. The data we have to play with are observations of stars. Now, if you think a bit, what do you see in a star that you don't see in the sun, in the spectrum? There are stars that are almost identical to the sun. We call them twins. Best example is a star in Scorpius called 18 SCO. Its spectrum is almost identical to the sun, but it differs in a very fundamental way. Namely, there's the signature of the gas, interstellar gas between us and the star, that's superimposed on the stellar spectrum as narrow absorption lines. And it's these narrow absorption lines which to a stellar astronomer is noise, to an interstellar astronomer is signal. Okay? And we're going to diagnose the signal. Okay? Unfortunately, we cannot sample all directions in space uniformly, like you would like to do in a simple experiment. You have to deal with real stars, and you have to deal with real telescope allocation committees. So as a result, we don't uniformly sample all of space. We sample what we can get. And the observations shown here in black and red, the red are just the newer stars, are our sampling of stars out in different directions in galactic coordinates. But we can only sample stars for this work with observations that are primarily ultraviolet, high spectral resolution. So we're forced to limit what we're doing to one scientific instrument, Hubble, and one spacecraft, and to one instrument on Hubble called the Space Telescope Imaging Spectrograph. Unfortunately, that's all the data really that we can play with. And when Hubble goes, we're in trouble. Okay, so here's what we do. Here's a high-resolution spectrum of two nearby stars, actually. Forget about the names. They just have astronomical names to them. And say, okay, what if we are looking at one star, so we have one sight line, and we have one ion, in this case, singly ionized iron, but we have many absorption lines of that ion. So what we see is these narrow absorption lines all lined up at the same radial velocity, about 15 kilometers a second. They're all pretty narrow, and they all line up very nicely. Okay, that gives us some information. That basically tells us the velocity of the interstellar gas relative to the sun. And if we can fit a line, get its equivalent width, we can measure the column density, the number of atoms or ions on that line of sight to the star. Two pieces of information. However, many stars show not one absorption feature, but two at different radial velocities, sometimes 3, 4, or 5, and sometimes it gets even more complicated. So if you're looking at this star, you can say, well, there's two pieces of interstellar medium gas in the line of sight, and they have different radial velocities, and they have different column densities. Okay? Got that far. Let's make it more complicated. Okay? Let's say we now look at the same line of sight. We have two different ions, iron 2 and deuterium 1 or whatever. We have multiple ions. Therefore, we can look at the line width, which is usually characterized by this quantity B, but think of it as full width half maximum, which is related to the thermal component, temperature over mass, and a non-thermal component that astronomers call turbulence. Don't ask me what that is. Okay? Now, if you have two different ions of different mass, then you can immediately separate a thermal component of the width from the non-thermal component. Okay? So that immediately says, we can get a temperature of that gas, and we can get its turbulence. And if we look at the same ion in different species, different different lines of that particular ion, some of which might be forbidden or semi-forbidden, then we can get densities, at least electron densities, and we can measure abundances, how much there is in that column density, and we can compare those abundances, for example, relating, let's say, iron to hydrogen, compare it to what's in the sun, and we can determine the difference and call it a depletion, and we can, in principle, even get ion fractions if you have, let's say, iron 2 and iron 1. Okay? Now it's getting more interesting. Okay? So let's go further. Okay? I have to get forward and backwards right on this. Let's say we're now going to look at not one line of sight over there, but a line of sight over here and over here and over there and up there. So we have multiple lines of sight. Okay? And for each of these lines of sight and for each of these ions, we get all these quantities. But now, what additional can we learn by looking in different directions and seeing if things correlate? Well, you get a radial velocity in this direction and a radial velocity in that direction, both of which are projections of the three-dimensional motion along the line of sight. And we can look out into space and say, well, are there regions of space for which the radial velocities follow the projections of a single velocity vector? Ooh. The whole thing is moving as if it's a steel ball, coherent through space, even though the densities are 0.1 per cubic centimeter. And guess what? It happens. That leads into the whole idea of global morphology. How are different parts of the interstellar medium moving with respect to other parts of the interstellar medium? Yes? Okay. When you measure an absorption line, again in the stellar spectrum, you measure a velocity in that line of sight. So it's a radial velocity, not a tangential velocity. It's a Doppler shift. Sorry. No problem. Doppler shift. I didn't use the word Doppler. Okay. And if you can go one step further, namely if you have global morphology and kinematics, these different things moving with respect to each other, then you can begin to come out with some kind of evolution, like the sun was in past in some idea, some part of the interstellar medium, moving in a certain way with certain abundances and certain column densities. And in the future, you can project where the sun is going to be moving through different pieces of the interstellar medium. Okay? So let's get there, at least as far as we can. Okay. As I said, we have many lines of sight. We measure the radial velocity and line on all these different lines of sight. And let's say, take a zeroth order approximation. What if all of the interstellar medium gas around the sun were moving coherently with one velocity vector? Okay? All moving together. What if? So you can take all the different radial velocities, fit them with a least squares law for a single velocity vector, and sure enough, you can now plot the observed velocities in kilometers per second against that predicted by this mean least squares zeroth order fit to all the data. And what do you get? Well, you get a fit. However, each of these data points has an error of about 1 or 1.5 kilometers a second. The spread is huge. And what's shown here in color-coded, for example, look at the red. The red points are those points for which the error is 10 sigma, the displacement is 10 sigma compared to the random error of measurement. So if you have a distribution of points for which 45% of the points are 10 sigma away from the mean, you know that this is not a uniform flow. Okay? What is it? Not uniform. Although on the grossness zeroth order scale, everything's sort of moving in the same direction, but the random motions are are large compared to the uniform flow. So, I mean, 45% of the points are 10 sigma away from the mean. I would like you to be a referee on some of my papers. No more comment than that. Okay, so what do you get? So let's start taking pieces of the sky here, there, and everywhere, and see if they fit a vector, a common vector within the error bars of the individual measurements. Okay? And we start playing with the data, and Seth Redfield is the real expert at this. And first of all, you know, if you take points that are very close together, then the different projections tells you nothing. You have to have data points that are, stars that are far apart in order to see if they have a common vector. And sure enough, we look around and we say, we have a number of data points, and wow, we find a whole group of data points covering a large piece of the sky that are all moving at the same radial velocities corresponding to a common velocity vector. This happens. And the structures are not simple spheres. The interstellar medium is not a whole bunch of spheres. It's we think, a whole bunch of long, thin structures that are filamentary. We give one example. I'll show you more. Again, structures that line up. Here's going, and then, of course, you have to rotate around to the other side of the sky, and they fill up. When you start getting down to structures that are only a few data points, we worry about it. But in many cases, we get large numbers of data points. Now we have structures, we have to give them names. Okay? We choose names for what constellation many of the data points are. So they have names of constellations. But I'm sure the IAU, when they get serious, are going to say, you've got to have some kind of telephone book numbers for these things. Okay, so what are the closest structures of the interstellar medium in terms of kinematics to the sun? Okay? One thing we find is roughly 40 or 50% of the sky, shown in red here, is moving coherently, velocity, with respect to the sun. And huge piece of the sky, and if you see essentially half the sky from one vantage point, that means one of two answers. Either you're just inside that structure or you're just outside that structure. Okay? Because if you're far away, the structure will be small in terms of angle, and if you're close, if you're inside the structure, well inside the structure, it'll cover the whole sky. Is that clear? So the real question, which we're going to get to, is the sun inside or outside of this thing? And since many people have thought we're inside it, it's called the local interstellar cloud. Okay? To be not yet determined whether it really is the cloud we're in. Okay, that's one big structure. Another big structure, sort of centered close to the galactic center direction, seen in projection towards Alpha Centauri, the nearest star, is called the G cloud, G for galactic center. It covers about 20 or 30% of the sky. And there's this filamentary thing over here. And here's another structure seen in projection towards another very nearby star, Sirius. Okay? And we give it a name, etc. Yes?
Inside the structure and the structure is closed.
Yes?
Then you cover.
Exactly. Therefore, you're right. Therefore, you're just inside it or just outside it. You're at the edge.
Outside. You were just inside.
Well, the question of whether we're inside or outside, at the end of my talk, maybe we'll take a vote. Okay? And I'll show you the data one way and the other. Okay? That'll be like a live homework problem. Okay, but now here's a question. What if, we see actually many of these clouds that are like filamentary type structure. If you see a cloud edge on, it's filamentary. What if you see it this way? So a cloud could be very thin, narrow sort of thing, but if you see it perpendicular to its axis, it looks large, covering a large piece of the sky. If you see it this way, it's thin, right? We have only one vantage point where we live. So the question of the real three-dimensional structure of these things is TBD, to be determined. Okay, but the universe is more complicated than that, at least even the local universe. Here's the 15 different structures we've been able to identify so far. All of whom have names, and I don't want to go into too much detail in this, other than point out, see these little X's with a circle? For each of the different clouds, which is color-coded, that's the direction from which the material is coming towards us. Now, of course, the sun is moving with respect to interstellar gas surrounding it, so the net effect of the inflow of the individual cloud directions, they're all sort of in this direction, coming from here, and the outflow, going out the back, all sort of here, which basically is another way of saying the Zerothorder, the whole interstellar medium around the sun, is all moving sort of coherently, but it has individual structures to it that have different velocities such that the inflow direction covers a piece of the sky. Okay? So, I haven't lost you yet. I'll try better. Okay. Since we have many lines of sight through the, quote, local interstellar cloud, we can determine its three-dimensional structure. Right? You know, least squares, 3 dimensions. Okay? So, here is the column density through the local interstellar cloud, or converted into if you assume a number density for the material, that'll give you a distance. Now, how large is this thing in parsecs? Parsecs. Very simple to understand parsecs. Parsec is about 600,000 astronomical units. Okay, so you can make that thing. Okay, so we are now looking out into the galactic space, galactic coordinates. This is the direction towards the galactic center. And what you see is a major piece of the sky, more than half the sky, has a very low distance to the edge of the cloud, or equivalently very low column density. And, you know, in other directions, we have the much, you know, 2 or 3 parsecs, so we're talking about 1 million astronomical units, or perhaps 2, to the edge of the cloud. Okay? So that's the view from us. But if you have a 3-dimensional model for this thing, you can say, let's put us at the geometric center of the cloud and say, well, what do we see? Okay? Let's do it. So, we're now at the geometric center of the local interstellar cloud, looking out in all directions. And of course, we see the column density, or distance to the edge of the cloud, in all directions. And you notice something interesting. There's a piece of the sky for which, you know, the edge of the cloud is very close to the geometric center. Interesting. What's there? What's in that direction, as seen from the center of the cloud? Okay? What do you think is there? No, we're at the center. We see this region of almost no absorption in the local interstellar cloud. What's off in that direction? Any ideas? Well, the galactic center is actually in this direction. The edge of the galactic disk? No. That's thousands of parsecs away. I'll give you a hint. Okay? The column densities that we're measuring are neutral hydrogen. In this direction, there is almost no neutral hydrogen. Ionized. How would it get ionized? Stars. What kind of stars? Hot stars. Oh! Here we go. Hot stars. Okay. What I now have added to this plot are 3 hot stars. In fact, this one, Epsilon Canis Majoris, is the largest source of extreme ultraviolet radiation in our local neighborhood, okay, as seen by the EUVE satellite. This is the biggest source of extreme ultraviolet photons. Beta CMA is the second biggest source, and Sirius B is the closest hot white dwarf that is a strong source of extreme ultraviolet. Extreme ultraviolet radiation ionizes hydrogen, right? Isn't it interesting that the 3 strongest sources of ionization of hydrogen just happen to correspond to the region of space as seen from the center of the local interstellar cloud that doesn't have any or very little neutral hydrogen? Okay, interesting. So, I mentioned we're working with, this is with work with Seth Redfield on coming up with 3-dimensional representations of the local cloud. I don't want to spend any significant amount of time saying, you know, we're doing projections, for example. If you're sitting in the galactic center and you look at the local cloud, then you see it's sort of split up and the shapes are not spheres. Nothing in the interstellar medium is a sphere. Okay, we're actually beginning to lay out the locations in 3-dimensional space of these different clouds with different names and their orientations. And this is work in progress. There's a real problem because when you see absorption due to a certain cloud in the direction of a star, you don't know where along the line of sight this material is. Is it nearby? Is it close to the star? You know, that's a big issue. So you have to do some guessing. But I do want to point out this arrow. This is the direction that the sun is moving relative to these interstellar clouds, and how far it'll move, the end of the arrow, in about 275,000 years. So you get sort of a feel of a time scale of moving through these structures of warm gas. So let's, okay. What are the properties of these clouds? This is the environment in which we live, so the environment in which the heliosphere lives. Well, there's a very important paper by John Slavin and Priscilla Frisch, 2008. I don't think things have changed much in terms of our understanding of the properties since then. So I quote their numbers. Neutral hydrogen density of about 0.2. And you wonder, how can large pieces of space move coherently if their densities are 0.2 per cubic centimeter? This is not a solid ball of iron moving through space. This is an extremely low density plasma, just happens to be moving coherently. I don't understand. But we continue. Electron density is of order of 0.07, so notice that the material is mostly neutral, but it's really partially ionized. Now, of course, the neutrality, dominance of the neutral is very important, because if there wasn't neutral material coming into the heliosphere, then there wouldn't be charge exchange that wouldn't produce a hydrogen wall, which we see in Lyman alpha, the previous talk. Okay? So we're talking about material that's partially ionized, temperatures 6,000, 7,000 degrees or so, which turns out to be a really interesting question. I'll explain later. Fractional ionization of about 0.2. Heating is primarily by ionization of hydrogen, producing photoelectrons that then heat the plasma. So this is extreme ultraviolet radiation from stars like Epsilon CMA, photoionizing hydrogen, giving these energetic electrons, well, thermal electrons, which then provide the heat and produce the temperature. Cooling is typically by forbidden transitions, for example, of carbon-2 and sulfur-2. Pressures, interstellar medium people talk about pressures divided by Boltzmann constant. Okay, so P over Boltzmann constant is about 2,000. And that's an interesting number, because often you think in terms of equipartition. Is there the pressure balance, between the magnetic field and the thermal pressure in the plasma in the interstellar medium? Well, there would be if the interstellar medium had a magnetic field strength of 2.7 microgauss, and there are indications that in fact it's larger than that, in which case the magnetic field determines the structure of these partially ionized warm clouds. That's an interesting idea. We haven't developed that. Okay, the inflow velocity of the material to the sun, that's including the sun's motion through the interstellar medium, is about 26 kilometers a second. This number is being debated right now, and I'll show it in a subsequent slide, and it has an important effect in terms of our understanding. And these calculations, okay, I now have to be honest and tell you, these calculations assume the local interstellar cloud is an ionization equilibrium, thermal equilibrium, and dynamic equilibrium, all three of which are almost certainly not true. Yes? Mean free path, well, of the hydrogen atoms or the neutrals, or the electrons? You know, I never did that calculation. That's an interesting point. I don't know. Definitely not?
In the neutral component, we're talking of order R6, something like that. So even for neutral collisions, they happen on distance scales of much bigger than the size of the heliosphere, but still much smaller than the size of these clouds.
Thank you, and a comment. It's always great to have a graduate student, even a former graduate student, because they keep you honest. right? Okay. Then, how do you measure a temperature? Okay? And I showed this formula before, namely the width of the line has a thermal component and a turbulent component. And so you look at different atoms. For example, here's a plot of deuterium as a function of temperature. So if take a line like deuterium, which is, of course, thermally broadened because it has very low mass. But you can say, well, it's either formed at like about 8,000 degrees if it's purely thermal, or if the plasma has zero temperature, then it's 8 kilometers a second, essentially turbulent, and everything in between. And so if you have a light element like deuterium and a heavy element like iron, they have a plot in different directions. So you can actually come up and say, aha, there's the temperature and the turbulence. Or to put it differently, here's a plot of the Doppler parameter as a function of the atomic weight of all these different elements from deuterium to iron, and they form a nice plot, and then you fit it with a temperature and a turbulence, and you get numbers like 7,000 degrees and turbulence like 1 or 2 kilometers a second. There are other pieces of the interstellar medium where you do the same experiment, you find they lie along pretty much a straight line, namely the temperature is low, close to zero, and the turbulence is high. Right? So we play that game. Okay, the kinds of temperatures that we find in interstellar gas near the sun, they're all in this range. What's shown in purple are the very best measurements that we have in terms of signal to noise. The mean value is like about 7,000 degrees. The turbulence, which is really how the material is moving in a non-thermal way, is like 1 or 2 kilometers a second typically. So the non-thermal motion is much less than the thermal speed. Okay, that's fine. Okay, we have these 15 different clouds. We have a range of temperatures. I don't want to go into detail on that. I do want to come back to the question of, are we inside or outside of the local interstellar cloud? So you have to pay attention to this because we're going to have a vote. Okay? I'm going to show 3 slides that lead to different answers. Okay? Here we go. What's shown here is, first of all, local interstellar cloud and the closest cloud to us, the G cloud, towards the galactic center. And what's shown here are the velocity of the cloud relative to the sun and the temperature of the cloud. So for the local interstellar cloud, at least for this paper, we had 79 lines of sight for which the mean value of the flow speed was 23.8 kilometers a second plus or minus 0.9. The G cloud, much different speed, 29.6, based on 21 lines of sight. Okay? Temperature, 7,500 degrees. This cloud, the G cloud, 5,500. These are real measurements. Okay? Now, Ulysses has looked at the inflowing helium from the interstellar medium. Now, helium is important because charge exchange is a big thing with hydrogen, but it's extremely weak with helium. So the helium coming in is not changed, deflected, whatever, slowed down, orientation changed by charge exchange. It's free flowing in. So it measures the direction of the inflow, and we can measure from the width of the helium line its temperature and its velocity. Okay? So according to Ulysses, and original work was by Witte and then summarized by Eberhard Mobius in a paper in 2004, is this temperature is about 6,300 degrees, and its velocity is 26.2 kilometers a second. Okay? Now, from that set of numbers, are we in the Lick or are we in the G cloud? How many think we're in the Lick? How many think we're in the G? Okay? 1. Well, at this time, Seth and I went off on the limb and said, we're not in either. We're sort of in transition from one cloud to the next. Okay? Based on the fact that the temperature is in between, of the helium coming into the heliosphere is in between these two, and the velocity is in between those two. Okay? IBEX went up, and it measured the inflow of helium into the heliosphere. Isn't that a bad idea? Helium into the heliosphere. But of course, the heliosphere was named because of helium. Okay. And he did analysis of the IBEX data and found that its temperature was a large range, 5,000 to 8,200, and its velocity was about 23 with large error bars. So question, are we in the lick or are we in the G cloud? Or are we in between? How many think the lick? How many think the G cloud? How many think we're in between?
Like 3 people voting.
Okay, well, let's continue. We're not finished yet.
I want to see that vote again. I want to see people admit.
Okay, how many think, based on this data set, that we are in the lick? Oh, that's quite a few numbers. How many think we are in the G cloud? How many think we're in between? Okay? Let's continue. I'm sorry, what? Okay, you really have to go back and read Eberhard's paper. It turns out that IBEX does not directly measure anything. It measures, there are degeneracies and there are assumptions, and you can say, well, it's this. If you assume a certain temperature, you get a certain velocity. If you assume a velocity, you get a certain temperature. Okay? Please read the paper. I don't want to misquote. Okay. Okay. McComas, who's the PI of the IBEX instrument, went through and did his own, comparing what other people in his team were doing, and said, okay, let's come up with a consensus of what IBEX is telling us about the inflow of helium. And in this paper, I think it's a science paper, it came out with a temperature now with much lower error bars, 6,300 plus or minus 390, and a velocity of 23.2 with small error bars. And now, are we in the, how many people think we're in the lick? Based on this data. How many people think we're in the G cloud? How many think we're in between? Okay. Now, I don't have a plot of the third piece of data, namely that Brian Wood has done. So I'll put Brian Wood on the spot and ask him to say he has reanalyzed the, essentially reanalyzed, let's go back. Essentially this data set, originally published by Vita, based on the Ulysses. And why don't you tell us, if you want to go off on a, we haven't orchestrated this yet, but if you want to tell us which way you think the new analysis of the old data is leading us.
The new analysis of the old data is mostly data from the Ulysses spacecraft, which also measured helium flow. Our reanalysis is also getting 26 kilometers per second, consistent with that value.
Yeah.
But we get higher temperatures of about 7,500 degrees.
Okay. This is not yet published. So now let's take another vote. Let us say, okay, according to the reanalysis of the Ulysses and new Ulysses data, actually, this number stays the same, and this number goes up to what, 7,200 degrees? Okay.
7,300 plus or minus.
So let's change this to 7,300 degrees. Okay? Now, are we in the lick? How many people think we're in the lick based on this new data? How many people think we're in the G cloud? How many people think we're in between? Okay. So I want to leave you with that mixed answer and make it very clear that we're not there yet, okay, in terms of understanding where the heliosphere is located with respect to the local interstellar cloud or the environment of the local interstellar cloud. Okay, but now let's see what comes next. Yeah. Where do I think we are? Okay, let me go back.
Nobody gets to tweet this.
Okay. My answer is stay tuned, perhaps in our lifetime. And the reason is the sun is right there, right at either just inside the lick or just outside the lick, and the direction of its motion is out of the lick. Right? So we can look at one of the strongest absorption lines in the interstellar medium, namely the resonance line of magnesium-2, 2796 angstroms. And what we see is absorption towards alpha Cen, which is sort of in the direction that we're moving. All we see is the G cloud absorption, not the lick absorption. So we can come up with an upper limit of the amount of absorption in the line of sight that we're traveling that would be lick. Okay? That's a tiny number. That's the column density. We now have a number density. Okay? That will immediately tell you a distance. We know the speed that the sun is moving in that direction. So if you have a speed and you have a distance, then you have a time, an upper limit to the time. Okay? So according to that calculation, the sun will leave the lick, if we're inside it, in less than 3,000 years. Perhaps tomorrow. So I say, stay tuned. We may know an answer. Okay. Now that I've piqued your curiosity in this, so let's go in the other direction here. Okay, we've played that game. Next game. If space is partially filled with these sort of warm clouds, what's in between them? If they don't fill all the space, there has to be something in between, which we don't see by looking at neutral hydrogen or ionized iron or ionized magnesium or whatever, singly ionized. What is it? Okay? And here is a wonderful object lesson of how it is that when theory and observation agree, we're in trouble. Okay? You think of it. The first ideas of what's between these warm clouds was based on a theory and an observation. The theory was, well, let's compute the theoretical properties of the interstellar medium. We have certain heat inputs, certain cooling, and what they came up with, this is going back to classic papers, of a three-component interstellar medium in which the hot component is 1,000,000 degrees. Okay? Observation. X-ray satellites look out into space. They see diffuse X-ray emission. They say, X-ray emissions must be produced by 1,000,000-degree plasma. Therefore, the region around the sun, aside from those areas that are cooler, must be 1,000,000-degree plasma emitting the X-rays. Theory and observation agree. Okay? When that happens, the funding agencies don't give you money. The telescopes don't give you observing time because there's already an answer. Right? Why keep observing? Why keep funding? The problem is the theory is based upon a whole bunch of assumptions that are not correct. And the observations, well, somebody on the XMM satellite decided, let's point this X-ray telescope at a comet. Now, comets are cold gas, of course. Looked at a comet and saw bright X-ray emission. How can a comet emit X-rays? It's not 1,000,000-degree plasma. Then they thought of it and said, well, the solar wind is fully ionized. The comet is ejecting all kinds of neutral hydrogen. There's charge exchange between the solar wind protons and the comets emitting neutral hydrogen. That charge exchange leads to X-rays. Okay? And then they said, well, it's not just comets that emit X-rays, but there's a lot of hydrogen in the interplanetary medium, and it sees essentially the solar wind, so there's going to be charge exchange producing X-rays. So you do a calculation, and what you find is that much, if not most, of the diffuse X-rays that we see looking in all directions is local. Okay? So, this was done, and I mentioned some papers by Snowden, for example, and Kutumtra, I think if I get her Greek name correct. And they basically say there's either little or no evidence of hot gas within a few parsecs of the sun. What is it? There's a real interesting paper by Barry Welch and Robin Shelton, 2009, in which they argue that it's really highly ionized gas, maybe recombining from a supernova explosion or wholly ionized by hot stars, maybe 20,000 degrees or so, but no neutral hydrogen. And then other ideas have been proposed that this is really Stromgren sphere gas. So I don't want to get into what's a Stromgren sphere other than say that near a hot star you have fully ionized gas and out to a certain distance, sphere, for example. And that was first discussed by Stromgren, and they're called Stromgren sphere gases. Okay, so that's a good question. What is in between these warm clouds? No, stop. I tell my students, there are no stupid questions. There are only stupid answers, and I'll try not to give one. Yes?
How do you know that these clouds have sharp?
You mean our sharp boundaries? We don't.
Why not just assume that there has to be a transition layer, and it might very well be in a transition layer which is sort of mixing two clouds?
Okay. It's a great question. There's a paper just coming out. I know it's in Astro pH. It's not. I don't know if it's yet in the Astrophysical Journal by Cecile Gree and Ed Jenkins, and they argue along your lines. Namely, you don't have discrete clouds. You have gradual transitions from one property to another. And maybe they're right. In fact, this is an argument that's going to go on for the next several years in the literature. And we're going to go back and forth on this particular issue. I suspect it's more likely discrete individual clouds because when we look at nearby stars, we see a velocity structure, velocity of the interstellar absorption, that's centered at one velocity and then another velocity, but not a whole range of velocities in between. Okay? That would be my argument.
How do you define a neutral cloud?
You have to combine it with magnetic fields. I mentioned before that equipartition, balance the thermal pressure against magnetic pressure, occurs at about 2.7 microgauss. There's evidence that, at least locally, the magnetic field is 3 or 4 or 5 microgauss. So the structure of the magnetic field will determine the structure of these, quote, clouds. But of course, the clouds are only partially ionized, so you're going to have ambipolar diffusion. It's going to be interesting out there. Okay? That's not yet settled. There are all kinds of PhD theses that have to be written on that topic. Okay? Let's go on. So I mentioned this. What fills space? Okay. That's not yet well determined. Okay. I keep getting mixed up going forward and back. Okay. This is sort of the final thing I want to get to. Let's compare the heliosphere today with the heliosphere under different boundary conditions, different environments. Okay? So let's start. Here's a plot done by Müller, Hans Müller, published in 2009, in which he did characterize different interstellar medium interactions with heliosphere. Okay? First, let's take the heliosphere today. Okay? Here's a plot of temperature versus distance, where the sun is now at 0. This is interstellar mediums coming in from the right. So this is 500 astronomical units coming in from the right, and headed out, here's 400 astronomical units in the backward direction. Sun is here. Here's temperature. Here's neutral, mostly neutral hydrogen density. Okay? What you see is, as the interstellar material comes in, there's a bow shock, or maybe there isn't a bow shock. That really depends on the strength of the magnetic field. It might be a bow wave, not quite a shock. But in this calculation, we'll call it a shock. Then there is the heliopause, which Brian showed was material. That's the separation between the flowing interstellar material and the solar wind material. And then there is the termination shock, where the solar wind goes from supersonic to subsonic. So it's supersonic on the inside, subsonic on the outside. Okay? And here's the density for conditions today, namely interstellar medium neutral hydrogen is about 0.2, we have the hydrogen wall. It jumps all the way up to about 0.4. Imagine the term wall for a density of 0.4 per cubic centimeter. Okay, and then you have very little neutral hydrogen. And of course, the reason of the hydrogen wall is charge exchange, which in effect slows down and heats the interstellar material. Okay, fine. So we have this kind of structure. We have a hydrogen wall. We have low amount of neutral hydrogen, and so on. What if the interstellar medium is really hot, fully ionized? Well, then the temperature is up at 1,000,000 degrees. I don't think there's 1,000,000-degree plasma nearby. It may only be 20,000 degrees. But let's just say, okay, fully ionized. If the sun moves into a region that's fully ionized, then we'll probably have a little bit of a bow shock. There will be a heliopause, but the temperature will be the same on both sides probably. And there will be a huge termination shock, according to these models. There will, in the density of neutral hydrogen, that's going to be this structure here, what we're going to see is neutral hydrogen in the lick. There will be essentially no, let's get it right. That will be ions. So this is the electron density, and this will be the, it can't be the neutral hydrogen density because there isn't one. Okay. Local bubble. Okay, for hot gas, the densities are all going to be low, and there's no hydrogen wall because there's no hydrogen coming in. Okay? A different world. Okay? Let's go further. Keep going in the wrong direction. Okay. People have gone out and looked with the Arecibo radio telescope measuring hydrogen spin flip transition. This is 21 centimeter. Okay? Looking out in all directions of the galaxy that could be seen from Arecibo and finding out where there's neutral hydrogen and what temperature it is. Okay? And individual data points are individual parts of the galaxy, or clouds you might want to call them, that have been studied in these 21 centimeter type measurements. And they're color-coded, and I'll describe in a minute. But there are maybe 100 or several hundred of data points for which there are not only location, but also temperatures. Okay? Cold regions of the interstellar medium are very small. So when if the sun were to move through a region of very cold gas, it'll go through it quickly because it's small. Hotter regions tend to be much larger, so it takes more time for the sun to move across a harder region. So what's plotted here is two things. First of all, how much time it takes to go through red, hot regions of the interstellar medium, blue, cold regions. And second, what's the size of the heliopause at the time in which the sun is moving through some of these regions? These cold regions have very high densities. High densities means high pressure. The heliopause is determined by a pressure balance between the interstellar medium and the solar wind. So when you're going through a dense region, the heliopause moves in. It's small. And when you're going through a region of much lower pressure, higher temperature gas that's much lower density, then the heliopause gets large. Okay? So notice, if we were going to go through cold gas regions, then the heliopause starts coming down to small numbers. Right? That's interesting. Let's take an example. Okay. Here's the local bubble. Local bubble is a piece of our galaxy extending out to 100 or 200 parsecs. So parsec is 600,000 AU. And it's a region of mostly ionized gas, except we have these warm neutral clouds near the sun, and it's surrounded in black color-coded regions that are cold, higher density gas seen, for example, in sodium-1. Right? And this is the view, let's say, from Okay, this would be the view from one direction, yeah, towards the galactic center, towards the north galactic pole. And notice this arrow. This is the direction in which the sun is moving relative to this piece of the interstellar, big piece of the interstellar medium, in the course of 12 million years. So roughly in, maybe something in the order of 10 million years, the sun is going to move into a region of much of cold, higher density gas. And if you go backwards, roughly 10 million years ago, the sun was in another region of cold, high-pressure gas in which the heliopause will be compressed very small. So let's go further. Okay. This is a great study. Seth Redfield is one of my former students, now assistant professor at Wesleyan University, and he wrote this paper with Catherine Wyman, one of his undergraduate students. Okay? And they did the following experiment. They say, well, we know which direction the sun is moving through space, so we know the direction in which the sun was moving through space. Let's look in the backwards direction and see towards stars in that direction how far it is that you have to go back in time in order to start seeing cold gas. Cold gas is measured by sodium-1 absorption. So they did it. Okay, and here's a plot as a function of several things. First of all, distance going back where the sun was, the time in years, millions of years going back in time. So nothing really happened in terms of sodium cold gas absorption till you get to about 10 million years ago, in which case you start seeing significant amounts of high density cold gas. And as you go back in time, you can see, this is also a function of radial velocity, you can see a lot more of this cold material. So 10 million years ago, and also 10 million years in the future, the sun's going to be in a region of really cold gas in which the heliopause is compressed down, and lots of things are going to happen. Cold gas, neutral hydrogen is going to be flowing in close into the inner solar system, including the Earth. Cosmic ray flux is going to be much, much larger. Okay? For example, cosmic rays destroy ozone. No ozone, no people. Okay. Okay. What is the nearest parcel of cold gas to us? Okay. People have been studying this, in particular looking at 21 centimeter out in various directions. And what they find is, this is work by Hylas and Trollin, is they found in this certain direction, galactic longitude and latitude, regions of space where there is cold neutral hydrogen. And what's shown is these dots are nearby stars in which the light is projected through the cold gas to us. There's a paper by Meyer and collaborators in which they've looked at several of these stars, and they find that this cold gas in these directions must lie between 11 and 24 parsecs, because at 24 parsecs you have a star where you see it, and a star in the same direction 11 parsecs away, you don't see it. So the cold gas is somewhere in between. So that's relatively nearby. Okay? Now the sun is not headed in that direction, fortunately, but what if it were? Okay? What if it were? What would happen? Okay? So, we have to make an assumption. We don't know the velocity of what the sun would be in that particular direction, but if we assume the velocity is the same as going presently through the interstellar medium, the density, neutral hydrogen density in this local Leo cold cloud, Leo because the constellation Leo, it's roughly 3,000 per cubic centimeter compared to the local interstellar cloud, which is about 0.2. So it's an enhancement of density of only a factor of 15,000. Okay? So where's the heliopause? Well, the solar wind pressure is, of course, going to decrease as 1 over distance squared. So the radius of the heliopause will be its present value divided by the square root of 15,000. That's an interesting number. 1.3 astronomical units. In other words, the whole heliopause gets compressed almost to the Earth's orbit. Right? That will have consequences. Let's go further. What if there were a supernova nearby? Supernovas produce huge shock waves out into space. And Hans Müller has done this calculation. Say, okay, let's put a supernova and take its typical energy of 10 to the 51 ergs and put it relatively nearby, 8 parsecs, and ask what happens. Okay? Well, you can compute the ram pressure of this supernova explosion at a distance of 8 parsecs. And what you find is it's going to compress the heliopause enormously. So here's a plot of density. Well, by the way, first of all, the Earth's orbit is 1 astronomical unit. So there's the circle of the Earth's orbit in terms of radius in the direction of the supernova explosion and radius perpendicular to that. And what you find is the density structure, of course, is going to come right into the Earth's orbit. And even more so, here's a plot where red indicates the material is purely supernova remnant material. White means it's not. Okay? So this supernova remnant material is basically going to come into the Earth's orbit. Supernovae produce all kinds of stuff that we're made out of. And one of the interesting things it produces is iron. And there have been measurements of people looking at what is down in the bottom layers of the ocean. And they find, you'll scoop up some of these bottom layers, and you find there's a lot of iron-60. Iron-60 is radioactive. It has a half-life of 1.5 million years. You can compare iron-60 to its daughters. I don't know what they are. Take the ratio, and you can say, aha, with that half-life, a supernova of this sort must have occurred and hit the Earth 2.8 million years ago. Right? And there have been more such events. So it's interesting how interstellar medium can not only interact with the heliosphere, but interact with us on the Earth. Okay. So, let's see, going backwards here. So, let me finish with actually the very beginning of what I said. Namely, we live in a very diverse environment, interstellar medium. Huge ranges of density and temperature. Things change since the Earth and the heliosphere moves through the interstellar medium. We're going to see very different structures over time scales of millions of years. But also, I mentioned with this interstellar cloud, local interstellar cloud, and leaving it, it might be tomorrow or 1,000 years. Okay. We live in this changing environment. And the environment is not just interstellar gas, it's also dust, magnetic fields, UV, X-ray, cosmic rays, supernova, ejecta, etc. Okay? So it's interesting to pursue this. Things will happen. You know, cosmic ray flux affects the Earth. It affects ozone. It affects habitability. And I want to leave you with the idea that solar physics, heliospheric physics, and stellar physics have a lot to learn from each other. And it's interesting to look at the interface of the two and how one field, interesting things in one field affects what's going on in another field. So I'll end with that and ask for questions. Yes?
So you put a paper that showed average electron density.
For the local interstellar cloud, yes.
Is there a sort of one or uniform measurements of
Okay. Seth Redfield and another one of his students actually did some measurements of trying to get measure the local the electron density in other of these clouds, these nearby clouds, and there's a range. But I think the real answer to your question is radio scintillation measurements. So people have gone out and looked at, for example, pulsars. Okay, and what you see is variations. That it's called scintillation. We see scintillation in the Earth because of, if you look at a star, it twinkles, right? And that's because you're looking through a highly inhomogeneous path through the ionosphere where the electron density changes on a rapid time scale, so the starlight keeps looking through different electron densities. So that kind of scintillation measures the variation in the electron density in the ionosphere. Same thing happens in the interstellar medium, and you can, by looking at pulsars and quasars and look at time variations, you can get an idea of not only the electron density in the interstellar medium, but also how it fluctuates and what spatial scales it fluctuates. Okay, spatial scales can be very small. I mean, much less than an astronomical unit. Yes, I'm not an expert in this literature, but I could point you in the right direction of people who are. Yes?
Research for the pulsar for supernova.
You mean, what star did it? Ah, well, I don't know of anybody who's actually pursued that, although I haven't gotten into the literature very deeply. Let me point out the following. I showed this local bubble, right, that we're inside of. Let me go back to that picture. Okay. We think the local bubble was produced by supernova explosions. Supernova explosions, of course, supernovae were massive stars, therefore young. Okay? So supernovae come out of young clusters of stars. Okay? And they have to be more than 8 times the mass of the sun. And these stars will live for, a few million years and then explode. Right? It turns out that in this neighborhood, roughly 100 parsecs away, is what's called the Scorpio-Centaurus Association. Okay? Whole group of young stars, many of which, and we also see neutron stars, which are the remnants of supernovae in this cluster. And you can calculate from the mass distribution of stars in the Scorpio-Centaurus Association that there must have been a number of stars of mass more than 8 times the sun, and therefore there must have been a number of supernovae. Okay? The stars in the association are of the order of 10 million years old. So on that time scale, there would have been a number of supernovae that would be in our neighborhood. But exactly which star did it, I don't know. I don't know the villain of the piece. Okay? Again, that's somebody who wants to really get deeply into this topic would be a great PhD thesis. Identify the villain. Okay? Or prove the theory right. Or wrong, as the case may be. Yes? Other questions? Yes?
I have 2 questions. Are there any stars within 8 parsecs?
No.
Okay, good.
We are safe for the moment. Yes.
Second question.
Well, actually, it's projected that the next star relatively nearby in the galaxy to explode will be Eta Carinae. And that's, I don't know, about 200 parsecs away. I think we're safe. But, the thing is more than that? Okay, I think we're safe on that one. But, the last supernova that went off the galaxy was Kepler's supernova, which I think is 1604. And, in the last, and of course there was one in the one of the Magellanic Clouds in our lifetime. It was like 20 years ago. Supernova 1987A, right? That was really bright. That was, you could see with the naked eye. But nothing within 8 parsecs. You can rest assured. You can sleep tonight.
Are there any measurements?
I don't know of any. Do you know of any? No.
Do we know?
I mean, one of the problems is that one of the reasons why stars can have non-detections of stellar absorption is too broad, and so interstellar column density is high. So one problem is when you move into one of these cold clouds, interstellar column density goes way up. And so I suspect that you won't be able to. Hydrogen column density is going to go. What answer?
Stay tuned. Maybe we'll come up with an answer to that in the next decade or so. Give me? Okay. Direct imaging. You've actually wrote you had a Hubble program to do direct imaging.
Well, yeah, I mean, the only direct images of astrospheres are those exotic, or, well, not exotic, they are, but just more massive winds from different. There's just no, there was one case, for a particularly compact astrosphere, for which we had a tentative detection of astrosphere by absorption. We said, okay, this is compact enough that maybe you can find an alpha emission coming from the hydrogen wall. So it basically, it was a long spectroscopy experiment. And we didn't detect it, and we actually argued that non-detection method is tentative absorption using traditional methods. But you have to have a very compact, or otherwise, it's kind of a surface plate. Barely on the level of detectability.
Okay. Any other questions? Okay.
More questions. We'll just break for about, say, 15 minutes. We'll come back.